Let us start our class today. For our just one thing. Stop share. Let us resume our class after your exam. Let me go through the another portion of your module, last module. The last module. Now, let us concentrate on the stress concentration. That is, you see, another method of future fracture mechanics. Now, what is stress concentration? First, we have to understand. While enjoying the stresses, you see, interesting the members like say torsion, compression, tension, compression, torsion, bending, etc. It is all so far we have assumed that the members don't have any abrupt change in their cross section. In your undergraduate syllabus, in your third semester syllabus, we have gone through different changes in the cross section area of the member. We have gone through the member is changing automatically, gradually from minimum to maximum or maximum to minimum. It can be of various type of cross sections, like from round, square, triangular, rectangular, etc. And we have also gone through few cases where the members is not changing its dimension gradually but abruptly. It is, say, you have of a certain cross section up to a length of say half of the 50 millimeter, 500 millimeter. Next, it changes to abruptly to another type of another cross section, say almost twice of the former one, and can be another change in the diameter or cross section area of the total beam bar. But actually, these are also the examples of abrupt changes in cross section. But there are other problems, other methods. I mean, other application of this abrupt change. We have gone through the members which are not changing their, we are not changing their abrupt, their cross section abruptly. But a taper member can be under tension, compression. The cross section varies uniformly. But there are examples where the cross section of the load bearing member cannot be avoided because there is some absorption change. There is some abrupt or sudden reduction in cross-sectional area. That is not exactly, that treatment is not exactly equal to the method of the changes in abrupt changes in cross-section, which was taught in third semester syllabus in strength of material. They are slightly different, but that makes a lot of difference in application as well as its treatment as such, its treatment itself. Now, abrupt in the cross-section, a load-bearing member cannot be avoided due to the point of view of application of its application. Its application means certain change of certain portion length of it, and then go back to the original length as it is. Maybe it is due to the ease in manufacture, or maybe due to the presence of certain other members which may be affected if the section is not changing abruptly itself at that particular position. Now, say a shaft subject to torsion. We have some shoulders like attachment to take up the thrust itself. And there are key ways for pulleys and gears. Key way means, say, think of a shaft itself. And on the radius of it, a certain portion of its surface, there is a rectangular cross section and rectangular hole, a blind hole, you can say, of certain length, not exactly hole, but a shape is formed over the surface of the beam members itself, where a particular particular block or prismatic block defined as key is introduced to make the shaft assemble with the gears or pulleys, which is supposed to be used for the power transmission itself. The shaft subjected to torsion will have shoulders, etc. That is the key ways of pulleys, and this is required for assembling the pulley or gears, etc. There are other instances of making an oil groove or groove for greasing of the surface of the different members itself. There are some certain holes. There is certain notches. These are common over the surface. These holes may be generally meant for lubricating the surface to after regular interval. Maybe they have a connection with a lubricating system, or you have to manually lubricate this holes in order to make the total lubrication of the surface itself. There may be notches. This notch may be engaged in certain other male members, may be engaged with certain female members, which makes another assemblies. But these are all the common type of abrupt change in cross section, common examples of abrupt change in cross sections. Now, elementary equations, if we derive under the assumptions of no abrupt change in geometry of the section, are thus no longer valid. You have to add it, you have to add, or what you'll say, you have to add certain complications, you have to add a certain other treatment or equations to get the right stress or stress which is in right loading introduced in the cross section, or to know the right maximum load which is supposed to be introduced in the cross section itself. Now, sectional discontinuities. This type of sectional distances are sometimes called stress risers. You see, just 1 second. Just known as stress concentration itself. This is called stress risers itself. The size of the shaft can be, say, like this. There is a shaft like this of certain length. And here there is a cross section like this, like here. The reduction in cross section, then it goes like this type of strength again. This type of reduction is generally causes the action of stress concentration, and this type of small discontinuities are generally defined as stress risers itself. And the stress distribution, this distribution of stress in the neighborhood of such regions are higher than other regions. You see, there the cross section is reduced to a certain extent. Sometimes this reduction can be considerably large in comparison to the parent cross section area, and that is thus such a abrupt reduction in cross section, which will result in abrupt rise in stress in this particular area, rather than the normal average stress distributed over the other portion of the shaft itself. And these regions are defined as stress concentration itself because generally it is a highly localized effect. Means this stress concentration have in this particular area and rather than in this area, because the stress concentration or reduction or stress condition here is extremely localized and extremely important to know in this but because it has a highly localized effect. Or in short, we are, due to our applications itself, or due to some lubrication purpose or some other purpose, we are thus reducing the cross section of our prismatic bar, and thus making it weak than the other portion of the shaft itself. Now, members are differently shown under in the next series here. The next members are which step concentration under tension and location is given in this following figure here. There is a step reduction here. Here is a one step itself. Here is one step itself. Here it is a one step. It is reduced here. This is much less in particular condition of the in the original. You can say the other part of the shaft itself. Now, what happens here? let the members can be circular. Let us consider that we are not considering the other type of cross-section, but at this point we are considered the circular cross-sectional members itself. Now, in the case of the member under consideration, say A1, A2, A3, the cross-sectional area of the portion ABC itself. Say A1, A2, A3 here. Here, A1 is here. A1 cross-sectional area is here. A2 cross-sectional area is here. And 2 and A3, the cross-sectional area is here. Now, what is the cross-sectional area? Thus, it is A, B, C, A, B, and C parts of the shaft itself. Now, if P is the axial tensile force, now axial and tensile force, we are not thinking of the tensile force itself. The stresses in the parts, according to the elementary analysis, you know, is P divided by A1 and P divided by A2 and P divided by A3 itself. So stresses here, it can P divided by the cross section A1, P divided by the cross section A2 in the section portion of the section B, P divided by A2 and it is here P divided by A3. It is the stress here. The shear stress in this by the elementary analysis are thus these values are valid in region for removed from the sectional discontinuities and which include the area where the load is applied. But these values are valid in the regions removed from the sectional discontinuity, including the region where the load P is applied. P is applied at the bottom here, you see, and according to the cross-section area, a different portion of this particular hanging shaft has different stresses. Here P by A3 at the portion C, at P by A2 at the portion B, and P by A1 at the portion A itself. Next. But the corners where the discontinuity occurs are regions of stress concentration itself. Although this P by A2 and P by A3 is valid for the full portion of the shaft, but the corners here, this like this here, here, this is the main area of stress concentration itself, because where from that it is abruptly changed, cross-section area is abruptly changing. They are given shown here in dots. And similarly, if we think of torsional member itself, the shear stress by elementary analysis are T by IA and TR by IA, where IA, you know, the polar moment of inertia of the sections A and B. If there is a torsional member here like this, it is a torque T. And here, as per the diameter, the polar moment of inertia is IV itself. And as per the dimension here, polar moment of inertia is IA itself. Just one thing, but it's only two. So, in the case of torsional member, here the stress concentration by elementary analysis of TR by IA and TR by IB itself, and T or TR is the radial torque at the portion at the total length of the shaft itself. As before, these average values are valid in regions far removed from the geometrical discontinuities. At the point of discontinuity and near about, the stresses are now rather high. This is available from different portion like here. It is far away from the curve, somewhere here at the end. But at the junction of these two sections, where the stress is uniformly reduced, it's entirely different itself. Here, the stress values for both the tension and as well as torsion is the maximum or high. Now let us go through the following instances. The members under tension itself. There's a figure shows a two-dimensional member having, it's a two-dimensional member. What one dimension is here, from here to here, from here to here, another dimension is from here to here. This two-dimensional member having two semicircular groups and subject to tensile loading. It is the loads are all shown here. This is a tensile in nature, and there is two semicircular deformation. That one is here and one is here itself. The distribution of the normal stresses now across this section, we can take the section MN according to the minimum portion of this cross-sectional area here, where the cross-sectional area is minimum. We take a section here at MN itself. Now point M and N, the stress magnitudes are much higher than the other points throughout this shaft from here or here. Here, this point M and M, it is the maximum itself. And it falls. Stress magnitudes are very high and they fall rapidly to uniform value as shown in the figure. You see, here is the maximum stress, here is the maximum stress, but here it is not that high. It is more or less equal to the average stress itself. But here at the end or at the lowermost part of this semicircular cross section, here the stress is maximum. Here the stress is maximum in comparison to stress here, and stress here. So it is the most vulnerable portion of this shaft at the at this particular area, at this cross section M, and at particular point N over the cross section itself. Now, if we, without taking into account of the stress concentration itself, the average of the normal stress across the boundary section Mn is given as sigma 0. What will be that? If you ignore the stress concentration effect, then average of the nominal or maximum stress across this section will be what? That is given as sigma 0, sigma multiplied by this is the stress here, which is given here, multiplied by the area, that is the width, as well as thickness is the T section with the, and divided by B minus 2R, that is the width minus 2 into R is the radius, the diameter of the section itself. From one R it should generate from this side and another R it should be generated from this side itself. B minus 2R is a reduction in cross section divided by multiplied by a T. So area here becomes B minus 2R into T, where the total load over the section itself, just 1 second please. Ashish. Yeah. हाँ, मैं just बात पूछना है कि तुझे आज से क्लास शुरू होगा कि नहीं? हाँ, okay. I'm just taking my class as we have last week we have been instructed. I will take both the class today. ठीक है? Yesterday was the holiday. Today is no holiday. That is some. Okay. I am coming tomorrow. In that Ishpat Express, so I will reach the river bed around 1 or 1:30. I will take the class afterwards. Okay? After reaching the river, I will take both the classes. Okay? Sorry for the interruption. Just 1 second, please. Okay. Doing share. You share just 1 second. Stop. Now, okay. What I've just informed you is that I'm just repeating it. Sigma 0 is sigma b into t divided by 2 PR means this is the stress sigma here multiplied by the width d and thickness t itself, which is the b is the thickness here as given here, and t is not shown, but the total load over this portion of the shaft is given by sigma b to t into b into t. Then if we divide it by the area here, where the width is b is reduced by b minus 2r, where r is the radius of this depression here. So b minus 2r multiplied by t is the cross-section area here. And if we divide the original load divided by this cross-section, this will reduce to sigma b by b minus 2r, which is the stress induced here at this portion of the cross-section itself. Now, at the point M and N, but this is actually the average cross-section, not average stress, not the maximum or minimum stress itself. Here we have to see that stress at the point M and at the point N are maximum, and let their values as sigma max. This sigma max may not be equal to sigma 0. Sigma 0 is the average stress throughout the length of the cross-section. But you know, in our advanced solid mechanics, we are interested to know the maximum or minimum stress itself. So let the value of the maximum stress is equal to sigma x. The ratio of sigma x to the nominal average value is called stress concentration factor. So this is the definition. The ratio of nominal or average stress sigma 0 is called stress concentration factor. This sigma x divided by sigma 0 is given as KT or stress concentration factor, or which is given as sigma max b minus 2r divided by sigma b itself. And if we put the value of sigma 0 as sigma b by b minus 2r, then it will become sigma max multiplied by b minus 2r, and in the denominator, it will be sigma into b itself. The subscription T, this is the subscription here. It explains in this stress concentration factor is often actually theoretically or experimental and does not depend on the mechanical properties or within the elastic limit of the plate material itself. So that's an important thing. This stress concentration factor, it is not dependent on the mechanical properties, like it is supposed to be within the elastic limit itself. It may not be within the elastic limit. It can be more than the elastic limit. But this portion, as per Hooke's law, all these stresses are supposed to be within the elastic limit. Only if it happens, only then the stress will be proportional to strain itself. And as per Hooke's law, condition of elastic limit is the must. But stress is not. But in case of the cross section here, M and N, the stress is not proportional. Here, stress may not be proportional to strain itself. and it is not following Hooke's law itself. So we have to calculate stress concentration factor can be theoretically and also can be experimentally, but it is not under mechanical property depending on the mechanical property of the elastic limit itself of this material of the material plate material. Sometimes what happens, instead of using the area Mn, the area away from the discontinuity is used to calculate the normal stress. So area somewhere here, not at the point M, not at the point N, but area sometimes here is used to across the Mn is sometimes used to calculate the nominal stress itself. So this is the nominal stress, average stress here, or a nominal or average stress. This average stress sometimes we may not consider the cross-section area in order to keep our job comparatively easier. So what we'll do, we'll calculate the nominal stress. In the present case, this will be sigma dash sigma bt divided by bt, or sigma or equal to sigma itself. What we are doing, we are multiplying sigma bt, sigma multiplied by b, the width, multiplied by t, the thickness. That means b into t is the area of the any cross section, and multiplied by the sigma, which is the stress induced in the member, and we divide by again the cross sectional bt, means actually the cross section area of any other places other than the section Mn, and thus the nominal stress sigma, nominal stress or average stress becomes sigma dash 0. Sigma dash 0 is equal to sigma itself. So in that case, nominal stress, if we think of certain area other than the stress concentration area or the area Mn, and it will become the nominal stress will be equal to the stress induced. Thus, we can convert this equation here, kt to the power kt dash is equal to sigma max divided by sigma itself. So while referring that to design tables, one should be careful about the meaning of the stress concentration factor. So stress concentration factor is given by the maximum or nominal stress divided by sigma 0, the stress at the cross section Mn, at this type of cross section Mn. That is the ratio stress concentration factor. But sometimes for our own practice, we make sigma 0 dash is equal to sigma equal to the nominal force, but without taking into account the stress induced in the area Mn. Then in that case, sigma kt will become to sigma max divided by sigma itself. Although sigma max may not be equal to sigma, because we are considering sigma max as the maximum stress induced in the anywhere in the beam itself, may be or may not be in the cross section Mn. But so sigma max may not may not be equal to sigma itself. So there is another stress concentration factor here in the design table, which is given as kt dash and equal to sigma max by sigma itself. So while referring to the design table itself, we can be careful about the meaning of the stress concentration factor itself. What is exactly the stress concentration factor and how we have to calculate it? We have to know it's a different way to calculate itself. Now, let us consider another two figure A1 and B. You say the radiation abruptly change are of high stress concentration. Regions where the cross section abruptly changes are zones of high stress concentration. Where you see here we are marked here, the zones of abrupt change in cross section is defined is the area of the stress concentration we already defined and discussed, and more or less it is the we are convenient about it. We are convinced about it. So here, the regions where the stress and abruptly change are zones of high stress concentration. To reduce the stresses, these regions are smoothened by fillets. Here, what we see, there is a abrupt change here. The cross section is here up from here rapidly reduced to here, and from here it is rapidly reduced here. There is no such fillets. Here is also same. From here it is rapidly reduced to this cross section. And in order to take into account the stress concentration, we have to use the fillets here, means rounding the cross sectional where it is abruptly changing here. So here we are abruptly changing the cross section, all right, but we are using a fillet here and fillet here. Now, this is so thus it is relevant. These regions are smoothed by fillets, as shown in the figure itself. Next figure here displays the qualitatively how the stress concentration factor in the plate varies with the ratio R by D. How the stress concentration factor is varies with the ratio R by D. This is the things. This is the shown in this particular graph itself, where R is the radius of groove of the fillet, means it is the radius of the fillet, not exactly the radius which I have shown here. And D is the width of the plate near the groove or the fillet itself. So here we are not thinking in this line where there is R is here the radius of this particular groove, radius of this particular groove at M, and the radius of the particular groove at N. Here we are thinking R is taken into consideration. R is equal to the radius of the groove, which we have already, or the radius of the groove or the fillet, and D is the width of the plate near the groove or the fillet. So what is the radius of this fillet is we are taking, not the radius of the reduction in length itself. And D is the width of the plate near the fillet itself, maybe somewhere here, in the near here, or somewhere here itself, means somewhere here like this. And D is the width of the plate and here the group of the fillet. So R and D are the most important factor. What is the maximum width of the group, and what is the diameter of the fillet, which is now become mandatory for reduction in stress and increasing strength of the in the strength of this prismatic bar at the time of sudden rejection in cross section. So our discussion, we have changed a bit. We are talking now with the radius of the group, and we are talking out now the radius nearest to the group itself, nearest to the plate, width of the plate, nearest to the group or the fillet itself. Now, the determination of the stress concentration factor now really depends from theoretical analysis for sectional discontinuity of several shapes. And it's difficult and complicated. The majority data for design purpose are obtained experimentally. So if by means of theoretical analysis, it is difficult to what is the exactly the stress concentration factor itself. And the majority of the data of design purpose are now obtained experimentally over different type of the different value of radius R by D, or ratio between the radius of the fillet divided by the width of the plate itself, or the diameter of the total plate itself. So we are plotting different values of R by D, so 0.1 to say up to 1 millimeter, and about the axis, and we are getting the value of this stress concentration and according to the ordinate equal to 1.0 to 1.4, 1.2, 2.2, 2.6, etc. like this here. And what we are saying, looking here, there we are getting two curves. Where is the stress concentration is given, factor is given for fillets for a particular ratio of D by D, and also what is the stress concentration ratio of near the groups itself, which is much higher than this stress concentration near the fillet itself, but somewhere at a higher radius of higher ratio of radius to the diameter, means deformation reduction in the area is comparatively less. Means the radius of the fillet is much higher, almost going to the equal to the value of the D, or the equal to the value of D itself. So there, more or less, the stress tension factors are same, but where the ratio is less, around 0.1, 0.2, which means the radius of the groove is much less than the width or main diameter of the fillet. These factors are completely different in case of fillet as well as for the groove itself. This is the groove, and this is the this is the fillet itself. This is the fillet of the same ratio, and this is the semicircular grooves where there is no fillet, but radius is all there. Here, radius is used as the radius of the particular groove, and here radius is R is used for the radius of the fillet itself. Here, for the groove, the stress construction factor is quite high, and for the fillet, it is comparatively much less than that. So, for the fillets, by application of the fillets, we are improving the strength considerably. But if such is the conditional application that only semicircular groove can be used, then our stress construction factor is much higher, which means the stress at the nominal stress at the junction at the stress construction area is much higher than the stresses at the normal force itself. Now, in case of a very wide plate with hyperbolical grooves, grooves may not be circle itself, may be hyperbolical in nature, it's like a hyperbola, and has been solved theoretically, and solution shows that stress concentration factor near the group of the can be represented approximately by this following formula. When the hyperbolic grooves for very wide plate is rather large, and grooves cannot be made just like a circle, semicircular. So it is the solution shows that stress concentration factor near the root of the grooves can be represented approximately by the formula Kt is the square root of 0.8 D minus 2R plus 1.2 minus 1. Means stress concentration factor is given under the square root of 0.8 D, where D is the diameter of the width or diameter if the plate is in round shape, or D is the width if the plate is flat in shape, divided by 2 into R, means the diameter of the stress grooved hole, plus it is at 1.2 is added to it under the square root, and out of the square root it is reduced by 0.1 by putting minus 0.1 in the outside of the groove itself, where D is so width of the plate or diameter plate at the groove, and R is radius of curvature at the bottom of the groove itself. So here we are using the width at the groove, width of the groove, not the total groove or total diameter itself, and we are using the radius of curvature at the bottommost of the groove itself. Hence, we are considering the radius at the maximum minimum width of the beam itself. Here, Poisson's ratio generally taken as 0.3 in the foregoing equation itself. Now, in the case of a circular member of large diameter with hyperbolic grooves and subject to tension itself, here a circular member of a large diameter with hyperbolical grooves and subject to tension, the maximum stress concentration factor occurs again at the bottom of the grooves. The stress concentration factor is given by Kt square root of 0.5 D by R. Here is 0.8, but it is half of the ratio of the width or the diameter of the groove here. So for a flat surface, a flat plate like member to a circular member, the equation is slightly different. Here, this ratio is taken, D by 2R is only half. Here it's almost 80% of the ratio is taken. Plus, in case of 1.2 is 0.85 is another factor added, and plus it is in case of 0.1 minus 0.01, it is 0.08 is added. So thus these two equations is seen. The stress concentration factor in the case of a cylinder under tension is similar to the stress concentration factor for the plate under tension. So cylinder under tension and plate under tension, there are two factors. They are more or less similar, but not exactly equal. So if d by 2r is 10 in